So I became the director of SAC-D back at the beginning of November last year. And I had spent the prior 6 years leading NASA's Hypersonic Technology Project. But throughout my career, going back into the 90s, I've been working in hypersonics. And it was back in the 90s that I met this young, energetic professor who had a degree, a bachelor's degree in Earth and Planetary Science and a bachelor's degree in Aeronautics and Astronautics and a master's degree in Aeronautics and Astronautics and a PhD in Aeronautics and Astronautics, all from MIT. And he was very energetic and very passionate about hypersonics. And I swear when you would see him in the hallway, he was practically at a run, going to the next thing, moving at hypersonic speeds throughout his life, which I think is how he has over 320 publications. Over the ensuing years, he became the chair at the University of Maryland and has now achieved the rank of Professor Emeritus. He's also been the longest serving chief scientist in the history of the U.S. Air Force. And he didn't stop there. He was also the director of the Science and Technology Policy Institute, part of the Institute for Defense Analyses. And from there, he became DDR&E, the Deputy Director for Research and Engineering for Modernization in the Office of Secretary of Defense, and the acting Undersecretary of Defense for Research and Engineering. So he's got the academic side, and he's got the government side. And then he moved on to be the Executive Director of the National Defense Industrial Association, and has just recently been named the CEO of the Purdue Applied Research Institute. He is a member of the International Academy of Astronautics, a fellow of the American Society of Mechanical Engineers, a fellow of the Royal Aeronautical Society, and an honorary fellow of the American Institute of Aeronautics and Astronautics. A very well-respected member of the hypersonic community, an advocate for NASA and its participation in national programs, and a friend to NASA Langley itself. He's been a frequent speaker here, and we're proud to welcome back Dr. Mark Lewis.
Thanks, Chuck. So listen to that introduction. I remember, when I was younger, I used to run. I don't run as much anymore. The hair's gotten grayer also, but I've earned every one of these. So first of all, thank you for the invitation to speak here. I have to confess, this is a really intimidating crowd to talk to about hypersonics, because there is so much history in this room and so many people who have contributed so much to this field. So I'm gonna tell you, I don't usually get nervous when I give talks on this subject. This time I'm actually a little bit nervous. So with your indulgence, I'm gonna talk a little bit about where we are, where I think we've been in hypersonics, where we are today, and maybe muse a little bit on where we've been. And when Vicki asked me to give this talk, she asked me to give a little bit of a personal spin on this. And so with your indulgence, I'll kind of interweave some career highlights, many of which intersect with the work here at NASA Langley. So I'm going to start off by saying, when I gave Vicki the title for my talk, I actually did the math wrong. I actually said it was a 35-year journey originally. Like, no, I backed up. Been actually at this at 37 years. So I've rounded up. It's almost 40 years in hypersonics. And I'll note that we've really gone from exotic thoughts of aerospace planes and single-stage orbit vehicles to much more practical cruise missiles and other...
Sorry.
That's okay.
I'll make it better for you. There you go.
How's that? Awesome, thank you. Much more practical concepts. All right, so I want to start off with a basic question of why hypersonics. And again, I suspect many people in this room could answer this question perhaps more effectively than I, but I tend to bookkeep it in several categories. One is space access. And for me, that's sort of the ultimate dream, the ultimate goal of hypersonics, to be able to reach space, but with an airplane-like operation, with the ease and flexibility of airplane operations instead of the overhead required for rockets. There are clearly military applications, and that's frankly where I've spent most of my career focused on the military applications. And there, hypersonics brings many attributes to bear. It's not just speed, it's just not just moving fast, but it's moving fast in the atmosphere, so I can maneuver, I can fly at altitudes that are hard to observe, and that leads to survivability. If I have a hypersonic cruise missile, for instance, it's harder to see, it's harder to track, it's harder to stop. That basically means that a hypersonic weapon is more likely to complete its mission than its lower speed counterpart. It means I've got rapid response capability, I can do precision strikes, and in the Pentagon we refer to something known as the OODA loop, which is the thought process that's involved in making a weapons decision. OODA stands for observe, orient, decide, act. You hear that often, especially among Air Force folks. And hypersonics really gets inside an opponent's OODA loop. They don't have enough time to figure out what you are, what you're doing, what your intentions are, to even come up with a response. I'll also note that there's, of course, interest in hypersonics from commercial entities. And right now, we've had a couple of companies that have sprung up that want to build commercial hypersonic vehicles. And, you know, we can muse about the practicality and the economics of a hypersonic airplane, but it's interesting to see that level of interest is once again peaked. So I'm going to start off with a curve that I think some of you will, again, be familiar with and will have experience. And I call it the Hallion cycle, named for the great historian Dick Hallion, who a number of years ago plotted out the funding cycles for hypersonics and concluded it's got about a 15-year periodicity. And we've got these boom and bust cycles. And again, I suspect many people in this room have lived this. If you go back to the late 1940s when we first started flying hypersonic sounding rockets, and then throughout the 1960s for the X-15 program, picking up in the mid-1980s with the National Aerospace plane program, which I'll have some comments about. And then after the end of the National Aerospace plane, the bottom kind of falls out of hypersonics. Side note, this center, I believe, was absolutely instrumental in keeping interest going in hypersonics. When the National Aerospace plane program ended and funding was cut, it was this center that really kept work going at a fundamental level, and also working with universities. And I was, as a young faculty member, I was one of the recipients of support from this center. So Langley has a long history in this, and a very proud history. I've noted in the early 2000s, X-43, I will say a few words about that, but that was a NASA Langley effort, which I consider to be the Kitty Hawk moment in hypersonics. And we flew X-43, then we flew X-51. It was an Air Force program, but working very closely with Langley. And then once again, the funding drops. But right now, you'll notice the line is going up. It's going way up. And I would argue we're kind of in boom times. I'll explain why we're in boom times. And I think that's going to continue. I'm very cautiously optimistic. All right, so if I can, let me talk a little bit about history. And again, I think this will be familiar to many of you. I want to start back in 1985. So I just finished my master's thesis. I was a PhD student looking for something interesting to work on. I did my master's thesis project on gas turbine engines in the MIT Gas Turbine Lab. And you know, I hate to admit, I hope there are no gas turbine people in the room, but I hate to admit it, but I kind of had this epiphany one day, which was, you know, we know how to build gas turbine engines. We're pretty good at it. They're the most efficient machines on the planet. I mean, you know, turbines are better than, 90% efficient. Compressors were close to that. Combustors were 98% efficient. And everything we were doing was like, to get that extra decimal place of efficiency. And I wanted to work on something that flew higher and faster and was more exciting. And around that time, the National Aerospace plane program was announced. President Reagan went on national television. He announced the program, got a little bit confused about what it was going to be. He kind of conflated single stage to orbit with Orient Express, but it was higher and faster. It was super exciting. And some of you may remember this picture, the National Aerospace plane. It began as a DARPA program, by the way, and then transitioned to its own project office. Once again, Langley was absolutely instrumental in that program. But I'll point out that in 1985, the National Aerospace plane program kind of looked like the slender configuration. That was the baseline design. It was going to be a 50,000-pound vehicle, single stage to orbit, reaching Mach 25 on supersonic combustion ramjets, taking off from a conventional runway. So I finished my PhD in 1988 looking at inlets that would fit on a vehicle like the National Aerospace plane. And I will tell you, when I first started as a PhD student, the first thing that our group did was take a trip from MIT all the way down here to Langley. And I was working at the time with a brand new assistant professor by the name of Dan Hastings, who's now the department chair at MIT, and a gentleman named Manuel Martinez Sanchez, who, if you know him, is possibly one of the 2 or 3 single smartest human beings on the planet. And their first step was to come down here and do an immersion day on what were the technical challenges associated with building this vehicle. All right, so I finished in 1988. I immediately started as a faculty member at the University of Maryland, started going tenure track. As I was getting tenure, so 5 years later, 1993, the NASP program was canceled. But note, when it was canceled, this was the NASP configuration. Again, I think many of you are familiar with this. And recall it had started at 50,000 pounds, and by the time they canceled it was 450,000 pounds, and the price tag was going to be $12 billion. And by the way, we still didn't know if the scramjets would work. I'll get to that later. We didn't know if it could take off. And by the way, we were pretty sure it couldn't make it to Mach 25. It could only make it to Mach 18 and somehow coast the rest of the way to orbit. Weren't quite sure. So the program got canceled. And in the aftermath, as you'll recall that curve, so did a lot of the funding in the field. Now, if I look at today, where I'm now Professor Emeritus, have been actually for a couple of years, kind of hypersonics is back, but it's back in a much more reduced scope, if you will. We're not talking about Mach 25, we're talking about Mach 5 or 6. We're not talking about single stage to orbit. We're talking about maybe 500 nautical miles in the atmosphere under scramjet power, under maybe rocket boost glide. And we're not talking about space missions right now, although hopefully we will someday again. We're talking about military missions. So if I kind of give you a synopsis of where we are today, I'm going to give you a somewhat rosy picture. No insult intended to Rosie Weinstein in the audience. And that is, we've got a lot of programs, and I think by and large those programs make a lot of sense. Last year, the General Accounting Office did a survey of all the Department of Defense programs. So these are just DoD programs, not the NASA programs. They identified over 70 programs. Now, some of these are relatively small. Some of them are modest efforts. Some of them are basic research efforts from the Air Force Office of Scientific Research, or Office of Naval Research. But several of them are significant programs with the goal of delivering real capability. The Army and the Navy both have boost glide programs. The Army is planning to deliver capability by the end of this year. For the longest time, the Army program was led by a 3-star general named Neil Thurgood, who was a force of nature. If you wanted to take a hill, he was the guy who was going to take that hill. And by God, under his watch, the Army was going to deliver by 2023. The Navy is working hand in glove with the Army. It's actually kind of a good news story. Your government at work, they're sharing information, they're sharing data. The Air Force had a program called ARRW, A-R-R-W, which was a boost glide. The Secretary of the Air Force recently announced that he wants to pull back on that one. We'll talk about that a little bit later. But they're moving forward with a hypersonic advanced cruise missile design using scramjet technology. And then a list of other programs. One that I'm especially excited about. When I was in the Pentagon, we set up something called the Joint Hypersonic Transition Office, the JHTO. It was congressionally mandated. Congress basically gave the department $100 million in its first year to set up this office. And one of the first things that the office did was create a university consortium, which now has over 100 universities lined up to work in hypersonics. It is led by Texas A&M. Rodney Bowersox is the principal investigator. I think some of that many of you know. But in addition to the universities, it's got about 100 industrial partners that are meeting with the universities. They're doing some really neat work because you've got university professors who are directly supporting industry concerns and issues. We've got graduate students and undergraduates and faculty members working on problems of direct relevance to ongoing programs. So that one's pretty exciting. I'll also point out there's a strong international effort as well. The United States is working very closely with Australia, for example, in hypersonics. I'm going to give a lot of credit to NASA Langley for that. And the reason is that one of the Australian leads in this is a gentleman named Mike Smart. And some of you may have worked with Mike Smart. He came from Australia, worked here at Langley, went back to Australia as a professor at University of Queensland, and has continued as one of the leaders in the field, and has helped cement that relationship very effectively. All right, so with all that good news, I will point out that, as is often happens in a democracy, you take 2 steps forward, 1 step back, and we're not entirely out of the hypersonic woods yet. I frequently get asked this question: will support for hypersonics continue? If you look at the budget, it's actually good news. I left the Pentagon in January of 2021. As Chuck mentioned, I was acting in the office of the Undersecretary of Defense for Research and Engineering, which, by the way, was really cool. I had the Missile Defense Agency under me, I had DARPA under me, I had the Space Development Agency. We put in a huge budget chunk for hypersonics. If you look across the 5-year plan, the DoD's got about $25 billion in hypersonics over 5 years. So it's a significant investment across the board. We set up the FY22 budget leading into 23, and then we were headed out the door. And I remember one of the last meetings I had in the Pentagon, we were meeting with the chiefs and the secretaries of the services, and we had all this money lined up, and I asked the question, so when the new team comes in, when the Biden administration comes in, are they gonna keep the funding there? And the then Secretary of the Army, a fellow named Ryan McCarthy, just laughed. He said, this budget is 700 pages. They're not gonna have time to make significant changes. And sure enough, the new team in the Pentagon kept that money intact. The real telling point was, would it grow when they released the 24 budget? And in fact, they did. So that's really good news. There's consistent funding. But having said that, there are some rocky shoals. About a year and a half ago, the Union of Concerned Scientists released a report on hypersonics where they questioned the value. Now, I have actually distributed their paper as an example to students of how not to write a paper. If anyone in this room had reviewed their work, you would have tossed it in the trash. You certainly wouldn't have recommended publication. I'll give you an example of some of the things that they did. They wanted to model a hypersonic vehicle. So they found an aerodynamic model of a DARPA vehicle, the HTV-2. So the HTV-2 was something that DARPA flew, and it didn't work. And by the way, it didn't work because of experiments here at Langley showed them it wouldn't work, but DARPA didn't listen. They flew it anyway, and it didn't work. But that's a whole other story. So they found the aerodynamic model that they used on the paper came from China. So it was Chinese researchers trying to reverse engineer a DARPA thing that didn't work, and their model was wrong. But even better, these researchers flew the model incorrectly. They flew it at a -4 degrees angle of attack all the way through its trajectory, so they doubled the temperatures, and of course, thermal signature goes with T to the 4th. So they got everything wrong. But boy, did they get a lot of publicity in that paper, including front page in the New York Times. More recently, about 2 months ago, the Congressional Budget Office picked up on that paper and wrote their own report, which basically mirrored everything that was in that paper. And when I saw that, I talked to a friend on the Hill. I said, what do we do about this? And she said, oh, don't worry, everyone ignores the Congressional Budget Office. But still, it's out there. And then more recently, the United States Air Force, I mentioned the Secretary of the Air Force, Frank Kendall, who's kind of been on again, off again on hypersonics. His predecessor was very much in favor of it, but Frank's been on again, off again. He announced that the Air Force was stepping back from their program of record, the Arrow program, because they've had some flight test failures. And those flight test failures had absolutely positively nothing to do with the hypersonic thing they were trying to test. But he is still stepping back in the program. You've also heard some skepticism. So very, very recently, I think in fact just yesterday, you heard that the Ukrainians were able to defend against a Russian hypersonic attack. And I've had so many people say, well, the Russians are using hypersonics in Ukraine, and it's not working very well, so doesn't that show that hypersonics isn't that effective? And my response is, no, it shows that the Russians build really crappy systems. So, but there's that to deal with. Lots of other questions come up. One of the last things I did as I left my last job was kick off a study on the hypersonics industrial base. Basically asking the question, do we have an industrial base in place that can satisfy the needs of the DoD if we're going to ramp up production? And the simple answer came back, no, we don't. And that's true for materials, raw materials, manufactured materials. It's also very true for workforce and test and evaluation capabilities. And then that leads into the whole issue of test infrastructure. There is an enormous ground test backlog. I think, again, people in this room are probably aware of that. Today, if you want to test a full-scale supersonic combustion ramjet, you got two choices. You come here to Langley, or you go to the Arnold Engineering Development Center. About 2 years ago, we had a period when the folks at Arnold Engineering had a problem with their facility. I think they forgot to turn on a cooling button switch, and they overheated their facility and said they were down for a couple months in maintenance. And so Langley was the only facility in the country where you could test a full-scale supersonic combustion ramjet. So that's precarious. You know, if that facility went down, we would have had a situation where we could not test this technology. Right now, industry is reporting if they want to get time in any of our major wind tunnels, they're looking at a backlog of at least 9 months. In some cases, several years. That's not a way to move quickly. And I'll point out it causes other bad problems. You know, if you do your wind tunnel test and you have a problem, your instruments don't work, whatever, you need more time, you're out of luck. There's someone lined up right behind you. If you do your test and you see some really interesting physics and you want to do more experiments, once again, you're out of luck. There's someone lined up behind you. So not a good situation. Flight test. We're also in a bad situation with flight test. We are flight testing on a very, very infrequent pace. All right, we're flight testing now at about 1/10 the pace of the Chinese, and I'll talk about the Chinese threat in a moment. That's bad from several standpoints, not the least of which is our workforce just isn't experienced in flight tests the way they used to be. And so you're seeing a lot of dumb mistakes being made. You're seeing wires being crimped and fins falling off. You're seeing safety officers who can't read checklists properly. It's embarrassing, but it's not surprising given that we don't have the experience. So these are all issues that need to be addressed. All right, so what is driving this big increase? My friend Paul Piscopo, who many of you know, likes to quote that there are three primary motivations driving humans: ego, fear, and greed. I sometimes add altruism to that list. But I think part of the thing that's driving us is ego, but more importantly, it's frankly fear, because we have some competitors who are marching very, very quickly in hypersonics. In fact, by almost any standard that I can conceive of, the Chinese have exceeded our capabilities. All right? They already have deployed systems, and they've shown us pictures of their deployed systems. You see in the lower left-hand side, in 2019, the Chinese did a military parade down their main street in Beijing, and they showed off their hypersonic weapons, their boost gliders. The Russians, they have deployed systems. As I mentioned, they're already using them in Ukraine. They're not very effective, and it's a stupid use of hypersonics, but it shows that they've got them deployed. Meanwhile, in the United States, we don't have any deployed systems. Every time we've made progress, we've kind of called a halt to things and slowed down. We've essentially given the rest of the world an opportunity to not only catch up, but move beyond. And these competitors, I mean, they're not even quiet about it. You can go on YouTube and see YouTube videos of Chinese wind tunnels. They've got a shock facility that's larger than anything that we have in the United States. And when they first announced they're building this facility, I had some wind tunnel colleagues who looked at it and said, yeah, it's going to be a really crappy facility. They don't have the right geometries. They're going to have bad flow conditions in the test section. And then they published in the open literature and their test conditions, and they're really good. The Chinese have been publishing CFD papers that are also really good. I mean, they've gone beyond just mimicking what we're doing and are being quite innovative. So all in all, a bit of a startling predicament. All right, so if I can, let me go back to some basic science, and again, I suspect it'll be old hat for many in the audience, but to get us all on the same page. As I think many of you know, there are two basic approaches that I can take if I want to build a hypersonic thing. Right now, one is air breathing, where I'm using oxygen from the atmosphere to power my engine. And the other is to put the thing on a rocket, usually as a glider. I get it up to some high speed, and I separate, and then I glide the rest of the way. The DoD is interested in both of these. Frankly, right now, most of the DoD effort has been on the right-hand side, on the boost glide side. I'm going to admit I'm an unabashed fan of air breathing. So most of the work I've done over my career has been on the left-hand side of that slide. And you're seeing the DoD slowly realize, yeah, there's actually a lot to air breathing, and that's really where we want to be. When I speak to DoD audiences, one of the things I like to emphasize is both of these technical approaches have value. There are things that rocket boost gliders will do that air breathers can't. There are things that air breathers can do that boost gliders can't. And so you really want a range of these technologies. Hypersonics can't be just one thing, even from the weapon standpoint. Let me explain why I like air breathing versus rockets. And I think the first time I saw this curve, it was produced by a gentleman named Tom Curran, who's a longtime chief scientist at the Air Force Research Labs Propulsion Directorate. And Tom basically plotted Mach number versus specific impulse, thrust divided by the rate at which fuel is consumed. And from here you see very clearly that at low Mach numbers, turbojets, turbofans do extremely well. As you climb up the Mach scale, ISP falls off. But the ISP of an air-breathing engine is always going to be better than a rocket for the very simple reason that on the air-breathing engine, you're not carrying the oxygen with you. So you're not bookkeeping oxygen as part of your fuel weight. So you can have a much more weight-efficient engine. The best specific impulse you can achieve with a rocket is in the high 450-second range. Gas turbine engines regularly go into the multi-thousand range. And even at the high Mach range, the specific impulse for something like a supersonic combustion ramjet, a scramjet, is going to be about twice the ISP of a rocket. So that, in a nutshell, is why you want to do air breathing. You go further in a tank of fuel. And you see this in many of the military concepts. For example, on a cruise missile, if you want a cruise missile to go far, you want it to have an air-breathing engine. You don't want to put a rocket engine on it. I also like to show, explain the classic ramjet curve. This is right out of the textbook that I learned propulsion from. It was Jack Kerouac's Aircraft Engines and Gas Turbines. I didn't learn from the 92 edition. I used to teach out of the 92 edition. But in a nutshell, if you plot out the specific impulse versus Mach number for a ramjet, there's always a peak specific impulse at some low supersonic Mach number. A ramjet produces no thrust at 0 Mach number because there's no ram effect, there's no compression effect. So it can't take off from the ground. You need some other engine. Ramjets lose thrust at the high Mach range. That's because in a ramjet, air comes in, it slows down, the air heats up, and as a consequence, you get above the combustion temperature. You can't burn fuel in the combustor. And the solution to that is you keep the air moving quickly through the engine. That's the secret behind a supersonic combustion ramjet. And in theory, you can reduce thrust right up the Mach scale. Ramjets and scramjets don't work at 0 Mach numbers. You need some other engine to get off the ground if you want to build something that takes off from a runway. So you probably have to go to some combined cycle engine technology. For most of the military concepts, especially for weapons, we don't worry about that, because if I got a cruise missile, I'm launching it off of a flying airplane, probably. It's got a rocket booster to get it up to speed, so I've solved the low speed problem. But if you want to move to an airplane or other concepts, you need something that's going to get you off the ground. All right, so let's talk a little bit about fundamentals. More than 20 years ago, as a faculty member, I wrote a proposal to this center, NASA Langley, and I had this figure in the proposal, which was my list of pretty much every fundamental challenge that we had in hypersonics. This was the full laundry list. And if I look at that list, it's pretty much still valid. There are a lot of problems yet to be solved in design of these vehicles, engine integration, optimal aerodynamics, leading edge physics, combustion physics, optimal trajectories, even the whole design process associated with hypersonic vehicles, because they're fully integrated systems. The engines and the airframes are very tightly coupled. But the good news is if I go through a list of all the key challenges, and especially the ones that I was focused on, I can show that we've made a lot of progress. So here's a list. When I finished up as a PhD student, this was my list of unknowns that I was interested in at the time. The first was, could we get a supersonic combustion ramjet to even work all the way up the Mach scale? Could an engine that was designed to fly at hypersonic speeds survive the creation of a strong normal shock wave and unstart the engine? Could you inject fuel? Could you mix it? Could you burn it at high Mach number? Would the leading edges survive? What was the state of the boundary layer? The flow right near the surface of the vehicle. Was it smooth and laminar? Was it turbulent? Where did it transition? We really didn't know. Area that I was particularly interested in, what would the flow to the inlet of an engine look like at hypersonic speeds? If you had a really thick boundary layer, what would it do to the engine? How would you be able to handle that? How would you integrate that engine with the vehicle? And on and on. Look at where we are in 2023. We've actually made enormous progress. We've flown scramjets now, and again, NASA Langley did the first operational scramjet flight. We haven't done Mach 18 or Mach 25 yet. I don't know if we ever will, but we've certainly flown Mach 5 and 6 and even Mach 10. Our hypersonic vehicles have survived engine unstarts. Scramjets obviously work. We know how to inject the fuel. We know how to mix it. We know how to burn it. We design leading edges that can survive the heat of hypersonic flight. We're still working on hypersonic boundary layer transition, but we know enough to be able to design around the uncertainties in transition point. And on and on. So overall, I think it's quite a record of progress and quite a testament to the work done at NASA, done in the Air Force, done in academia, and done in industry. One area that I really want to focus on, because this is an area that's near and dear to my heart, is design of optimal aerodynamic shapes. And through much of my career, I worked on configurations that were based on something called a wave rider, where you design the vehicle so it rides on top of the shock wave that it generates. And I had many students, many graduate students who worked on this concept, again, mostly with support from NASA Langley. And now I think it's generally accepted that almost any vehicle we would design today, especially an air-breathing vehicle, would be derived with a wave rider type geometry, where the shock wave is attached to the leading edge. All right, so let me come back to a little bit of history. You see on the right-hand side a picture of the X-43, which flew 3 times, first starting in 2002. Oh, I'm sorry, I had that wrong. Yeah, 2002. The vehicle was launched, a fin fell off the booster. Had nothing to do with the hypersonic vehicle, but that flight test was a scrub. But then in 2004, X-43 achieved Mach 6.8 flight. And then it flew again in November of 2004, reached almost Mach 10. That to me was absolutely remarkable. That's the Kitty Hawk moment in hypersonic flight. I will tell you, in my later years, I've been working a fair amount with former NASA administrator Dan Golden, who's quite a character, by the way. And Dan, for those of you who know him, you know what I'm talking about. Dan, as you will recall, was the NASA administrator who before X-43 flew, and he lists this as his greatest contribution as NASA administrator. And remember, he saved the space station. He introduced faster, faster, better, cheaper, all these things. But when you sit him down and say, "What was the best thing you did as administrator?" that's what he points to. So I think that's quite a tribute to the program. I'll also point out that the idea behind the scramjet also dates to has origins at NASA and NACA. So the very idea of a scramjet, the first credible paper on a scramjet, came out of Lewis Field, the NACA, 2 researchers by the name of Weber and McKay. And they wrote this wonderful thought piece about what would happen if you took a standard ramjet engine but kept the air moving at high speeds with that engine. And it's a beautiful paper to read, because they got most of the theory right. And it kind of took basically 46 years to get from their original paper to the flight of X-43. I will also note that there were lots of people who claimed to be the inventor of the scramjet. If their names aren't Weber and McKay, they're wrong. So make a note of that. By the way, I pulled out one quote from their report, which is: "The possibility of replacing the conventional ramjet inlet and combustor by a combustor having supersonic inlet velocity is thus suggested." I love that quote, because yeah, it was suggested, and by gosh, it actually worked. This is the X-43 vehicle, and I want to foot stomp this. This was a Langley creation. It had a wonderful origin story. There was a program at Langley to develop a hypersonic vehicle that could fly anywhere in the world in under 2 hours. It was a program based on a design by came out of a team led by a gentleman named Bob Pegg. A woman named Lana Couch, who I'm sure many of you remember, became the champion for this program. They had done it. There was a study done on what that vehicle would look like. I was privileged as a faculty member. I had some graduate students who were supported to work on this program, so we helped on the aerodynamic design. And then when there was an opportunity to do a flight test, Langley stepped up. Chuck McClinton was I think the lead technical person on this program. Langley stepped up and said, "We've got a vehicle to flight test," and that became X-43. The X-43 legacy was continued with this program, X-51, and I was in the Pentagon as X-51 was getting ready to fly. X-51 is very similar to X-43 in that it was subscale, scramjet powered. It was different in that X-51 was powered by a hydrocarbon fuel, whereas X-43 was powered by a hydrogen fuel. And because X-51 was hydrocarbon, lower Mach number, so Mach 5 versus Mach 10, but it had the advantage of being actively cooled. So X-51 could basically fly as long as you kept it fueled. X-51 was
On X-43, you basically soaked heat into the walls of the engine, and it just didn't fly long enough that you worried about melting the engine. X-51, you had active cooling in the engine, so it could pretty much fly as long as you fueled it. An X-51 flew 4 times. The first time was mostly successful. We had many members of the X-43 team working on X-51. I had the privilege of sitting next to Randy Voland, who had worked on X-43. When we did that first flight, and I couldn't resist. X-43 had flown 11 seconds in its flights. When we got to 12 seconds on X-51, I just kind of turned to Randy and said, "Beat ya," but we all had a good laugh about it. Second and third flights of X-51 were not successful. The first one was an unstart. The second one was an unstart. The third one, basically a fin fell off the booster. That happens a lot in hypersonics. Fourth flight, 2013, was wildly successful. The most exciting thing about that flight was that if you compared the data points that were required in flight to the data that had been acquired here at NASA in the 8-foot facility, they lined up beautifully. I mean, it just showed we understood how to engineer these systems. Now, having said that, let's go back and ask what happened after the third flight of X-43. You guys canceled the program. I mean, I was at Dryden at the time. I'm sorry, Armstrong. It'll always be Dryden to me. I was at Dryden at the time, standing on the roof of the control building, watching the B-52 come back. It was dropped off of a famous B-52 called Balls 8. Again, it's an airplane I'm sure many of you are familiar with. It had dropped the X-15. It had done a whole series of flight experiments. It was a Pegasus launcher. B-52 comes back. Gordon Fullerton, astronaut Gordon Fullerton, was the pilot. He does a wing wag. It was the last flight of that B-52. There wasn't a dry eye anywhere in the control center. I was standing next to the then Associate Administrator for Aeronautics, Vic Labatt, and Fred Gregory, who was the Deputy Administrator, was on my other side. And I said, "Guys, you need to continue this program." And I got sort of, well, yes, we see the value, but we don't really see the mission. So NASA moved on. I was at the celebratory party after that last flight. It was the most depressed group of people who had just accomplished something incredible that you'd ever seen, because they were being scattered to the 4 winds. Guess what? The U.S. Air Force did the exact same thing. So what happened after the fourth flight of X-51? Did we celebrate and say, all right, more test flights, more development, we need to expand the envelope? No, the Air Force actually stopped flying this thing. And even worse, handed all their funding over to DARPA, and DARPA decided, oh, hypersonics is interesting, and they started afresh. So the result is, the next time we flew a scramjet was in 2021, 11 years after the X-51 flight. And the reason is because, well, it's the nature of DARPA. They don't want to take over someone else's program and keep flying it. DARPA wants to do new things. So they did something new, which kind of reset the clock. Now, the good news on this is a picture of the Raytheon Northrop concept for Hawk. And I said, this one is actually moving forward to, it looks like a program of record. The Air Force is putting a lot of resources into this, as I actually believe they should. I can tell you that in my last Pentagon role, we did a lot of wargaming in hypersonics. And I'll tell you, bottom line up front, here's what we found. When we played out major scenarios, and you're not supposed to talk about which country your major scenario is, so we'll call them the red team. So when we played out scenarios against the red team, we found the following. When the red team had hypersonic capabilities and the blue team did not, the red team won, period, end of story. If the red team had hypersonic capabilities and the blue team had hypersonic capabilities, then the team that won was the team that had the deeper magazine. In other words, it becomes a war of attrition, and whoever's got more missiles wins. So one of the big advantages for air breathers is, first, they're cheaper than the boost gliders, they're smaller, they package better. You can get more of these into a bomb bay of an airplane. The boost gliders, if they're air launched, have to sit out on the wings. They ruin stealth capabilities. So for many reasons, I'm convinced this is a technology that we need to be pursuing. All right, almost wrapping up. I want to kind of wind down with revisiting some of the themes that I mentioned, but also offer what I call a little bit of tough love. which is what are we doing wrong? And I'll highlight some of the points that I already made. First, this on-again, off-again funding cycle has not done us any favors. It has allowed peer competitors to just move ahead of us. We made it easy for them. We even wrote papers, and I was responsible for some of this. We wrote papers declaring how important hypersonics was and the military value, military utility of hypersonics. In 2014, the Chief of Staff of the Air Force, General Mark Welch, did a call to the future, describing the Air Force of the future, and he highlights technologies. The number one technology he highlights is hypersonics, and they've got this wonderful vignette with an attack using hypersonic weapons, and that was openly published. So the U.S. Air Force says hypersonics is key to the future, and then doesn't really invest in it. And so the folks in Beijing and the folks in Moscow were very happy to read that, and they saw an opportunity. They did a whole of country investment. But it's even worse. It impacts workforce. In some ways, I was very fortunate being in academia that I wasn't, just like NASA and HIPOSR that kept funding going. I was able to keep graduate students going in this field. But if you look at industry, you see these ramp ups and then these ramp downs. And that is happening over the history. Today, all my friends in industry say, we can't find the people to hire in hypersonics. Yeah, duh, because you had the workforce, and then you let the workforce go. I've already talked about the loss of infrastructure. If this were a classified talk, I could show you a plot of wind tunnels where I compare Chinese wind tunnels versus U.S. wind tunnels, and the slope of the lines have the same magnitude but opposite signs. All right, we were decommissioning wind tunnels at about the same rate they were building new wind tunnels. One of my examples of how far we've fallen behind, I spent many years working with a wind tunnel just north of Washington, D.C., the Arnold Engineering Development Center Wind Tunnel number 9, Hypervelocity Wind Tunnel number 9. Beautiful facility. It was originally built by the U.S. Navy to study reentry systems. It got handed over to the U.S. Air Force in the mid-1990s. It's now operated out of Arnold Engineering Development Center. I know NASA's done a lot of testing there. I know the Orion capsule was tested at Tunnel 9. Why is it called Tunnel 9? Why number 9? Well, because, not surprisingly, it's the 9th in a series. That series began with Tunnel number 1, which was built by Werner von Braun at Peenemünde. And after the war, a team went over, they scoured Peenemünde, they found this one tunnel, they dismantled it, and they rebuilt it bolt by bolt in the United States. Actually, there's a great little story about that. The Army Air Corps wanted the wind tunnel, and they crated it up, but they didn't know how to ship it back. The Navy had a ship, so the Navy got the crated boxes, shipped it back to the U.S., and reinstalled it at a Navy facility, what was then the Naval Ordnance Laboratory. Happy to say that Air Force Navy cooperation is a little bit better these days. But, so tunnel number 1, 1946 is when it was operational. Tunnel number 9 was built and dedicated 1976. So we had a period of 30 years in which we built 8 new tunnels. Since 1976, we have built no new tunnel facilities at that complex. So think about that. Now, yeah, we've updated the instrumentation, obviously. The control room has been modernized, the instrumentation is modernized, everything's been modernized. But that shows you we've really kind of dropped the ball on our facilities. All right, I'm also gonna point out in my tough love list, one of the things that we as a community, I think, have done to ourselves is we've tended to oversell things. I mean, remember that National Aerospace plane? We're gonna do Mach 25, single stage to orbit, take off from a runway, do a mission, land on that runway, be ready to take off again. I mean, it required at least 3 miracles. But it didn't stop there. I mean, actually before the National Aerospace plane in the 1960s, there was a very similar program called the Aerospace plane. It was different than the National Aerospace plane, had many of the same problems. But even when I was in the Pentagon the first time in 2007, we had this program dropped on us from DARPA called Black Swift. And Black Swift was gonna be a Mach 6 hypersonic vehicle that was gonna fly up to, it had to fly up to Mach 6 from any runway. It had to do a barrel roll. We had no idea why DARPA wanted to do a barrel roll, and then come back and land on a runway. I remember the time, so I was in the Pentagon, and Chuck McClinton calls me up and basically starts yelling at me, "Where's your integrity? You can't build this vehicle." I'm like, "Hey, I'm on your side on this one. It's not ours." But that was the same era. We had just flown X-51. We could have put more investments in X-51, but instead we were looking to this next thing that required several miracles. And on and again. We've done some poor program choices. When the Air Force looked at operationalizing hypersonics, they could have chosen either air breathing or boost glide. They chose boost glide, which I think was a mistake, although one that they're correcting now. We've had hubris in the field. When DARPA was doing its HTV-2 program, originally, DARPA wasn't going to do any wind tunnel testing. Now just step back and think about that. They're going to fly a hypersonic vehicle without ever putting in a wind tunnel because they had confidence in the CFD codes. And I know there are CFD people in this room, and you're probably cringing at that thought. And indeed, it actually came down to a bit of a battle at the time between the Air Force and DARPA. And the Air Force found, and we put our foot down. We said, if you don't put it in a wind tunnel, we will pull out of this program. And so there was a bit of urinary Olympics about that. But we finally got an agreement from DARPA. They put it in a tunnel here at Langley, and discovered, lo and behold, that they had blown their boundary layer calculations and the heating calculations on the vehicle. Ultimately redesigned the vehicle. They flew it. It failed because they didn't do enough wind tunnel testing. The part about this that I love is that the program manager during the flights was different than the program manager who was seeing the program in the initial phases. The program manager, once it flew, basically right after the first failure, calls up various wind tunnels and basically says, how much wind tunnel time do you have available? Money is no object. And they put it in the tunnel and tested it and found the flaws in the design. I've already talked about the problems with insufficient flight testing, so I won't foot stomp too much on this, except to say that right now, we have about a 50% failure rate in our flight test programs, and that's if I'm being generous. And what do I consider a failure? I consider a failure to be one where we don't even get useful data. All right, if you fly it and it doesn't work, but you'll learn something useful, I'll give them a check mark on that. We've got a 50% failure rate where the booster doesn't light, the fin falls off, the cables were crimped. We actually had one case, I alluded to this earlier, where we had a range safety officer who couldn't read a darn checklist, and so accidentally activated the flight termination system prematurely. So, and again, it's not surprising. We've seen a lack of systems engineering, lack of systems thinking, and then the other one that I will foot stomp. Actually, 2 points that are related. We have failed to follow through when we had successes. When the technology worked and we could have built on it, we didn't. And instead, when we did move forward, we had next programitis. We wanted to go on to the next thing before we had fully fleshed out the previous thing. All right, so let me end on a positive note, which is, I think a really interesting development in recent years is the interest in hypersonics coming from outside government. Lots of money from government, but money now from outside government. And I'm going to highlight two because I'm kind of involved in both of these, so these are near and dear to my heart. On the upper left-hand side, you see a picture of a vehicle that is called the ROC, the ROC. It is currently the world's largest airplane. It's got the largest wingspan of any airplane ever built. It was not the most massive airplane ever built. That was the Antonov 225 that the Russians blew up in Ukraine. Right now, it is the most massive airplane. It's basically the size of two 747s glued together with a center wing section. ROC was the brainchild of billionaire Paul Allen. He was one of the billionaires who wanted to go to space, and his idea was to have a really large airplane that could launch rockets up to orbit. Paul Allen passed away. His family didn't want the company that Paul Allen set up, so they sold this airplane on pennies on the dollar to a company called Cerberus Capital, headquartered in New York. Cerberus Capital is run by a gentleman named Steve Feinberg. I call him billionaire Steve, but not to his face. Steve is an amazing guy. He is the ultimate patriot. He wants to put his fortune to work on behalf of national defense. And he got all the briefings on hypersonics, so he said ROC is going to be used for hypersonic flight testing. So right now, as we speak, the folks at Straddle Launch have built the vehicles that you see underneath that picture. I'll conclude with an actual photograph. They built a vehicle called Talon, which is a hypersonic flight test vehicle. A wind tunnel in the sky, but it's also a vehicle that can be used to test out other things, signatures, for example, And they want to go into the business of repeatable, recoverable hypersonic flight test. On the lower right-hand side, you see an announcement about Purdue University, my employer as of yesterday, which is building a hypersonic ground test facility. And here they're building out enormous capabilities, including a facility that will test combined cycle engines ultimately. But more immediately, they've acquired an old facility called Hypulse. It used to be up in Long Island at Gazelle. They've moved it to Purdue, and they're building a building around it. It's going to be a classified facility just off campus to do further hypersonic testing. They're also building something called a quiet supersonic tunnel, which is ideal for doing measurements in hypersonic boundary layers. So really interesting investment, and most of that money is coming from the state of Indiana, by the way, with some matching funds from corporate America. All right, so concluding slide, where do we go from here? I think we're on the right track. Speed bumps along the way. But I think we're finally realizing that hypersonics is a field we have to pursue, but not just onesies, twosies, not just demonstrations, but something we can deliver at scale. That means weapons in large numbers, that means cruise missiles, that means boost flares. Ultimately, I think we're moving in the direction of reusable systems, first recoverable, then reusable, maybe aircraft, maybe combined cycle engines, some companies that are working on alternate propulsion flow paths. Lower right-hand side, you see a picture of that dark vehicle. It's something called Skylon. It's the brainchild of a UK-based company called Reaction Engines, which is a whole different approach to high-speed propulsion. Essentially, it's a liquid air engine. So they use cryogenic fuel in a heat exchanger to condense air, separate out liquid oxygen, burn it in a conventional engine. Really interesting concept. Reaction Engines has opened an American subsidiary that is headquartered in Colorado, and they're pursuing this technology. The key is building a heat exchanger which can condense air as the vehicle flies. And they've made incredible progress in building extremely efficient heat exchangers with eye-watering efficiency. And then ultimately, I want to draw your attention to, I will still maintain that the brass ring of hypersonics is airplane-like operations into space. I suspect I'll never see this in my lifespan, my lifetime. I think my grandchildren will. I hope they will, because I'm still convinced that is the ultimate way for us to reach orbit. And with that, let me thank you for your attention. I'm going to close. That's an actual photograph of that airplane that I was talking about, the Stratolaunch Rock. As you can see, it is a mind-bogglingly large airplane. The hypersonic vehicle that they're going to be test flying, the Talon, first flight now is scheduled for mid-September, this coming fall. But it drops off of a pylon that's mounted at the center wing section. The lifting capacity of this airplane is also mind-boggling. I joke, it can actually carry the weight of an entire B-52. So if you want to do flight testing on a B-52, you can carry it on the rock and then drop it. Can't handle the wingspan, but if you can figure out a way to fold the wings, it has the lifting capacity. But at any rate, I think this and other solutions, including companies like Kratos, that are pursuing hypersonic flight testing, I think that's going to establish us with a rhythm and a flight cadence that will actually ensure a healthy future for the field. So with that, let me thank you for your attention again, and I'd be happy to entertain any questions that you have.
Yeah, Mark, I'm Craig Oldhurst. I actually worked in this area here from 1980s until I retired.
Yeah.
I was a materials engineer, so leading edges and everything.
Yeah.
And like on the Mach 10 X-43, I was involved with making the leading edges for those things. But a couple of questions I have.
Yeah.
One is in terms of the test facility. You say is any of this new money that's going into hypersonics going into new test facilities?
Actually, yes, and that's a really good news story. So there's an organization in the Pentagon called the Test Resource Management Center. I'll tell you why it was set up, and it's got a funny little NASA history to it, as it turns out. So in the late 90s, you may recall there was a push to shut down the the NFAC out at Ames. And I at a time, as a still wet behind the ears faculty member, wound up on a committee that was chaired by the then DDR-NE, Ron Sega. to look at this issue. And we concluded that the DoD said we needed it, and NASA said, well, we're not going to use it anymore. So the Air Force wound up with the wind tunnel. But it also got people in the Pentagon thinking, we need an organization that can kind of look across, if not the whole of government, then at least the whole of the Pentagon to manage test facilities. So TRMC, Test Resource Management Center, was created to do just that. So that you didn't have, say, the Army making unilateral decisions about tunnel facilities that, say, the Air Force and the Navy were using. All right, fast forward to 2023. They now have a stick, if you will, on managing facilities across the department. They have a crap ton of money right now on hypersonic facilities. Their director is George Rumford, who is a national asset. Hypersonics is the top of his priority list. Not just in wind tunnels, by the way, but also in flight tests. They've got a program called Mach-TB, which is a flight test program. And one of the things that I'm really excited about that program is they want to link the flight test to the ground test. So it's it's a full cadence, kind of what was done in X-43, kind of what was done in X-51. So it's actually kind of a good news story. There's a lot of catch-up. Don't get me wrong. And you look at the Chinese facilities, just look at the numbers and the capabilities, and it's intimidating. But I would say there's progress being made.
The other question I had, that was regards, you mentioned Texas A&M.
Mm-hmm.
One of the concerns that I had in a lot of my colleagues was that many of the grad students are foreigners.
Yes.
They're not, and so it's always leery trying to work with those guys, knowing that their grad students were not American.
Yes.
Is that being resolved?
Yes.
Also?
So it's a very complicating issue, and I'll start off by saying there are no simple answers. We always want America to be the country that the best and brightest come to. And if you look across the board, the overwhelming majority of foreign students who come to study in the United States want to stay here after they come. That's true even of countries like mainland China. More than 85% of the students who study here from China want to stay here. Some probably for bad reasons, but most because they just love the spirit of innovation and the freedoms that they experience. So you don't want to, I would argue, you don't want to shut down the pipeline. In fact, I'd say even worse. If you ever get to the point where foreign students don't want to come here, then that's when we really have problems. When the best and the brightest from around the world want to study in Beijing, not in the U.S., that's when we've got a problem. Having said that, we need to be realistic, and you're absolutely right about challenges with having some foreign students. So when we set up that university consortium, we established the principle that all the faculty members in that consortium, who work in that consortium, would have to allow first review of publications, review of nationality of students, and also there was a screening of the faculty members. And they had to sign up to that. Now, we had some universities that said, no, we can't do that, you're infringing our academic freedoms. I had 2 universities, including my alma mater, call me up and say, we're gonna need a waiver. And I said, no, I'm sorry, there are no waivers here. Or we can't participate. And we said, well, I'm sorry, then you can't participate. But we had a coalition of the willing. I mean, we had schools like Texas A&M, University of Illinois, Purdue University, Colorado, they basically said, yes, we understand the complexities here, and we want to work with you. So I see it not only as an example of how this can work, but as a model for other technical areas as well. So we're making progress. And I advise universities, I'm going to tell universities, look, I mean, I hate to say it, DoD's where the money is right now. The S&T budget for the Department of Defense this year is going to be about $120 billion. So that's where the money is. And if you want to work with the DoD, these are things you need to take into consideration. Okay.
What are your activities at Purdue?
Oh, what am I doing at Purdue? So, as I said, I'm 2 days into it. But Purdue basically brought me on board to create something called the Purdue Applied Research Institute, which the simplest description is Purdue wants something like the Georgia Tech Research Institute, or something like an applied physics lab. So the idea is to leverage research on campus, but to do national defense work, do international work, do some venture capital. There's a whole section that's going to be doing infrastructure. So PARI, as the organization is now called, Purdue Applied Research Institute, is a wholly owned LLC that is under the umbrella of Purdue. No, I am not moving to West Lafayette, Indiana, or more correctly, my wife is not moving to West Lafayette, Indiana. Therefore, I am not moving to West Lafayette. So we've opened up a DC office or trying to create a presence there. But really, really big emphasis, as will not surprise you, in hypersonics. On June 6th, we're going to be dedicating a new facility called the HARF, the Hypersonics Advanced Research Facility, which is a whole new facility that's going to have a Mach 8 quiet tunnel. It's got the high pulse facility that I mentioned. Purdue has staked out hypersonics as one of its core areas. Yeah.
We have questions from remote. Let me get this. We have a couple of questions from our audience that are
Sure.
remote. Damodar, are you ready to ask your question?
I sent the question, I think it is with Dave Hinton.
Oh, so, okay, so I have a test with two questions, that came on test. One is, on a scale from 1 to 10, where's the current state of technologies such as thermal management, propulsion, aerostructures, and materials?
7.35. So it depends on the application. Obviously, X-43 worked, all right? There's no question. X-51 worked. Hawk works. So we know how to do Mach 5, we know how to do Mach 6, we've got the engines, we've got the materials in that Mach number range. I actually think the most important challenges that we've got now isn't the science in that area, it's actually the engineering and specifically getting the cost down. So I'm often asked the question, why would you want a hypersonic military? Why would you want a hypersonic weapon? I counter it in the following way. I ask, why wouldn't you want a hypersonic weapon? All right, if I could take your standard cruise missile, take your Tomahawk cruise missile, Mach 0.7, and if I could reproduce all the attributes of that cruise missile, but instead of Mach 0.7, it travels at Mach 5 or 6 or Mach 7, why wouldn't you want that? And the very obvious answer, I'll answer the question for you. The very obvious answer is if it's too expensive. And I can't tell you how many times I would hear that argument in the Pentagon. It's too expensive. We can't afford hypersonics. So first, I don't think that's true. Scramjet is a relatively simple engine once you work out the design. It's got very few moving parts. Costs are in the material and some manufacturing, but you ought to be able to build these things at not outrageous cost. I'll also point out, but the Chinese and the Russians have figured out how to build these things at reasonable cost, so why can't we? But it really comes down to, if I were to invest, the single most important investment right now is getting the cost down. Getting the cost of materials, manufacturing. That's the key for adoption of this technology. So that's why I say, maybe in the 7 or 8 range. But engineering challenges, not science challenges.
Okay, and then there was one more question. Who leads and is moving fastest in hypersonics now? And what would you think the answer would be 5 years from now?
Ooh. So right now, I hate to say it, but it's China. They have done a whole of country effort that's eye-watering. They consider hypersonics to be as important as their nuclear program. The investments that they've made in building facilities, in universities. So I'll tell you a quick little anecdote. In 2016, we did a study with the National Academies on kind of the threat posed by foreign hypersonic efforts, and then briefed it. It got a lot of attention at the time. At one point, we were briefing the then Chief of Staff of the Air Force, and we're going through, and he's seeing the foreign threats, and there was one slide that the briefer had, which had a list of universities that work on hypersonics. And the briefer goes through it very quickly, and the chief's like, wait, stop, go back to that. And he looks at this long list of universities and says, that's how we know they're serious. This is the long-term investment. So the Chinese are there, and they've already got deployed systems. I think we've taken this seriously, and I think we're moving very, very rapidly. When I look at the programs that we've got right now, I'm really very confident. I think in 5 years, we'll have certainly regained the lead. And, I don't want us to just match someone for the sake of matching them. We need to go beyond that. So I'm actually pretty confident. But there's this window right now. Remember, we all talk about 2027 as being the time that we think, that China themselves has said, well, they want to be prepared to invade Taiwan by 2027. You think about how hypersonics would play. I mentioned wargaming, for example. What does hypersonics do for the Chinese? It holds all of our assets at risk. All right, think about a hypersonic attack on an aircraft carrier, right? Anyone know how much an aircraft carrier costs? Care to take a guess?
10, 12 billion?
Yeah, it's a good number. It's actually a little bit more. The Eisenhower class carriers are coming off the line at about 14 billion. That's just for the ship. Then you put the airplanes on board, that gets you up closer to 20 billion, and then you got 5,000 people on board, and then you got all the support ships. Imagine if you lose one of those. And the Chinese have obviously put a lot of thought into our vulnerabilities. How do you beat the U.S. Air Force? I will still declare no Air Force in the world will match our Air Force airplane for airplane. You put one of our pilots in one of our airplanes in the air against any of their pilots, any of their airplanes, we'll win every single time. So how do you beat us? Keep us from taking off. So hypersonic attack on runways, that would be a pretty darn effective way to counter U.S. advantages. And again, we've got peer competitors who are clearly thinking that way. So it's kind of scary right now where our competitors are.
Thank you very much.
Oh, can I take one more question? Okay.
I guess it's related to really the cost issue,
Yeah.
industrial base.
Yeah.
I mean, to be able to make high-speed vehicles, you have to have high temperature materials. You know, people have experience designing structures, and our industrial base in that is pitiful because there's no commercial application for it of the hypersonics.
That's right. And you look at some of the things, like one of the ways that we figured out how to get the cost of, say, scramjets down is to do advanced manufacturing capabilities. Additive manufacturing, for example. You want to build the cooling channels in a scramjet. Additive manufacturing is a great way to do that. We don't have much experience in doing additive manufacturing at scale. And even worse, we look at the programs that we've had previously. So I'll give you another example. I mentioned the DARPA HAWK program, the Hypersonic Air-Breathing Weapon Concept Program, that led to the current cruise missile activities. So I had one of the contractors tell me that when the program was ramping up at DARPA, they had over 100 people working on scramjets. And then they delivered their scramjets to DARPA. And then they were no longer delivering scramjets. It was a demonstration program. So they ramped back down to 5 people. So it's a workforce issue as well, but it's the capabilities. And then you look at all the materials that are required, all the high temperature materials. You look at the source of those high temperature materials. Lots of issues that we need to confront if we're going to deliver at large capability.
Quick question, Dan.
I will defer to the moderator.
Since we weren't able to record, is it possible we would be able to get a digital copy?
Oh, absolutely, absolutely. I think you've already got a copy of my slides. So happy to do that.
I'm also recording it on a cell phone. We'll see how that turns out.
We gotta go on. I'm sorry. We're running late. Thank you very much.
All right, thanks so much.
And I'd like to give you a complimentary
Thank you.
LAA
Thank you
mug.
very much.
Thank you. That was stimulating.
Thanks.